So good morning, everyone. As Florian kindly introduced me, my name is Christophe Basso, and I work for Future Electronics. I joined them in July 2021. And today we have a 1-hour seminar. It's all about active power factor correction simulations, and it will take us around electrical designs for single and three-phase networks. As you can imagine, as in any subject in power electronics, PFC is a very vast territory to explore and encompassing many different fields. So this is more or less a high altitude overview of what you could find in single phase and three-phase PFC applications. So this is the agenda for today. It's quite packed, so you guys buckle up and here we go. So you can see here the simple resistance connected to an outlet on the left side. Let me start the pointer mode. So the apparent power absorbed by a load, which is supplied from a sinusoidal source, is made of real and imaginary parts that we designate as active and reactive power. The active or average power, P, is expressed in watts and characterizes the physical work that is being executed, like, powering an incandescent light bulb or a big motor, or physical work, we call it. The reactive power, Q, is expressed in watts, volt amperes reactive, and it corresponds to a part brought by capacitive or the inductive components of the load. It does not exactly participate to the active power, but it increases the circulating RMS current. And when you combine mathematically P and Q, it leads to the apparent power, what we call S, which is expressed in volt amperes or VAs. And if you do the ratio of the average power to the apparent power, it determines what we call the power factor of the load, which is abbreviated PF. So on the example, when you have a resistive load which is connected to the mains, Q, of course, is 0 because it's a purely resistive load. And it implies identical apparent and active power, 70 watt in this example. And if you do the math, the power factor in that particular case is exactly 1, it's unity. Now, if you connect an AC-DC adapter, which also absorbs roughly 70 watt of average power, but it features a front-end rectifier made of a diode bridge and a capacitor, the average power, okay, we consider that the efficiency is good, so keeps nearly the same as with the resistive case, but the RMS current is much higher than in the previous case, bringing a large apparent power. And in this case, PF is barely equals to 0.6. The power factor, which is less than unity, and you see, as I said, larger circulating RMS currents for a given active power. So if I take the example of an AC outlet whose maximum RMS current is specified to 15 amps, like in the US, for instance, you could only connect 3 250 watt workstations in the given example, provided they don't have any power factor correction stage. Now, if you insert a PFC stage, a power factor correction stage, as a front-end stage, sometimes you will see the term AFE for active front-end, for each of the workstation and bring their associated PF close to unity, then the nominal input current drops to 2.3 amps for each computer, and you can connect up to 6 workstations now. The burden on the power cord is also reduced, and you can use a smaller wire gauge for the assembly. That's also another motivation for having power factor front-end stage. This is a classic you can find on the web, and I found it amusing for including in the presentation. It's another way of looking at the impact of a low power factor, which implies the circulation of an unnecessary high RMS current. As mentioned, the reactive part does not participate to the intended physical work as average power does, but all the current anyway circulates in the wires and overheats them. So the same for the glass here. The foam is nice looking, but does not extinguish your filth. However, it requires a large glass of beer, and the foam, while a smaller can could be enough, just for the liquid part. There's no need for having such a big glass. And utility companies encourage their customers to reduce the amount of reactive power by correcting the power factor of their high power equipment or an entire building, for instance, in an industry. And as shown in the reported example, if the PF is less than 0.95 here, the utility company charges a higher price for the energy that is delivered. And utility companies having a poorly maintained electrical network, depending on the part of the world we talk about, also are keen on pushing for power factor increase considering the risk linked to a high circulating RMS current, which can potentially bring fires on unbalanced facilities. This is also a classic where you see different wave shape. And after a few lines of algebra, the power factor can be expressed by the product of two parameters. We call them KD, the distortion factor, and K phi, which is the displacement angle. So if we assume a sinusoidal source, when the current is also sinusoidal, but phase shifted by an angle phi, the power factor is equal to cos phi. This is the classical formula you see with pure sinusoidal waveforms. And when the current is distorted, but with a fundamental still in phase with a sinusoidal input source, the PF is linked to the distortion factor as shown in the right side graph. And the power factor correction circuitry will then shape the input current to make it sinusoidal and in phase with the input source. You try to emulate a resistance more or less. There is an international standard that tells you the amount of harmonic that is authorized, and it's going by harmonic content. Actually, it's the IEC 1000-3-2, and it defines the measurement conditions and harmonic limits for the European mains. The harmonization actually took place in other countries like Japan, China, UK, etc. But PFC is not a requirement for US market, for instance. However, many manufacturers do include a front-end converter to reduce the input RMS current to reasonable values. As I said, you can use lower wire gauges for the power cord, and also they can export the product to other countries. And as DC-DC converters used in workstation and TV or monitors absorbing more than 75 watts, they fall under the Class D category, and they must limit their harmonic signature. The instantaneous power, so it means you do the product of input and input current and voltage signal. When it's absorbed from the mains, is the product, as I said, of the input current by the input voltage. And the result is modeled by a square sine wave, whose average value is the power transformed by the load into physical work, the average value, right? This is this component you can see here. And you see that sometimes when you actually plot that instantaneous power, sometimes you have more than the average and sometimes less than the average. And actually, if we plan on developing an active power factor corrector to emulate the resistive behavior, then the PFC circuit will need to also store and release energy as illustrated. And this process, this active process, results in a voltage ripple that appears on the output, and the frequency is twice of the input source, like 100 hertz in a 50 hertz or 120 hertz in a 60 hertz network. And for stability reason, because you don't want the loop to react on its own ripple, then you will unfortunately have to reduce the crossover frequency much lower than this ripple value, usually to a few hertz in a classical single PFC application. We'll see that in three-phase, that low frequency ripple has disappears, and it allows you to push crossover at a higher value. In a balanced three-phase system, the total power that is absorbed from the grid is the sum of the individual power supplied by phases A, B, and C. And if you plot these individual powers separately, as you can see on the right side graph, you classically obtain the square sine wave, of course, the individual contribution, but when you sum them together, you have a flat line, as you can see here, okay? And there is no low frequency ripple in theory when you use a three-phase rectifier. So in theory, the theoretical need for storage releasing energy as in single-phase application, emulating a resistive load, does not apply with a three-phase PFC. Here, this is an example that shows you the low frequency output ripple between single and three-phase PFCs, both of them delivering 3 kilowatt power from a 120 volt input line. The single-phase output shows a grid ripple with a peak-to-peak value of around 40 volts, and the output capacitor could obviously be a little bit increased, but that is not a problem with the three-phase PFC, and you can see on simulation it's flat, 100 volt DC, completely flat. You can use also an average model, and that's the cool thing. You have average models for single phase, as you can see here, or I extended them to, there is nothing new here, it's been modeled years ago, but I used the PWM switch model here in LTspice for, this is a 6-pack type of PFC, and you have 3 average models. It goes up to even 6 for Vienna rectifier, but you can see by using these models, you can run a transient large signal type of simulation, and you obtain here the variable you can have here with this single phase PFC, and you can see the ripple and the low frequency RMS content, while in the 3-phase PFC, you don't have that low frequency ripple. Of course, this does not take into account the high frequency ripple from the downstream DC-DC converter, but at least very quickly here, you can have an idea of the amount of ripple that is contributed by the low frequency portion in the single phase PFC. So let's have a look now at some of the typical architectures you can find in a PFC converter. You can find plenty of structure, right? But the traditional active PFC circuit uses a boost converter. That's the most common one. And the idea here is that because the inductor is in series with the input line, if you control the inductor current, you control the input line current. The boost, I would say, in most of the design that I've seen in industrial version or consumer market, it largely dominates the market, particularly in consumer electronics. And in the boost converter, as I said, the inductor current is the input current. Therefore, if you impose a sinusoidal envelope to the inductor current with constant up and down slopes, this is an important remark here. If the up slope and the down slope, so it means you truly have triangular waveforms on the inductor, then if the envelope is sinusoidal in borderline type of conduction, then the average current is also sinusoidal. And this technique lends itself well to implementing PFCs in various conduction modes, as we will see in a moment, or for power levels ranging from, let's say, 100 watts to several kilowatts in case of multi-phase structures. We're talking about single-phase type of application here. And as expected, the upper ripple is affected by 100 or 120 hertz ripple, and its amplitude will depend on power and the bulk capacitor value. If you look into a classical single-phase boost PFC, you always have a front-end diode bridge, which rectifies the input voltage for providing a positive voltage to the boost converter. And this bridge affects, of course, efficiency by dissipating power and cost, almost 2% of the budget in this 300-watt example. The diode bridge disappears in what we call a totem pole PFC or TP PFC, which processes the input voltage according to its polarity. So in that case, you no longer have diode, but you have one active high frequency RF bridge in the left side, what we call the fast leg, and a classical low frequency diode RF bridge in the right side. And when a positive cycle is applied, so you have a specific logic that decodes the input line polarity, transistor Q2 is actuated high frequency with the correct switching pattern, while body diode of Q1 acts like a control rectifier. Diode D4 is a low frequency type, permanently conducts during the 10 milliseconds of the positive cycle. And you can also have synchronous rectification on this diode bridge, of course. It could be the body diode of a classical super junction MOSFET. When the input polarity reverses, Q1 now switches at high frequency and D2 becomes the control rectifier. D3, in that case, is the low frequency rectifier and conducts during the 10 milliseconds of the negative cycle. In this type of circuit, it's very important to decode the line polarity and drive the active parts accordingly. The TP-PSC structure has been known since the 90s, but only has become popular recently owing to the introduction of wide bandgap transistors, featuring zero or low switching losses when recovering from conduction in the third quadrant. Okay, these guy here must be transistors or must be devices with a diode featuring very low reverse recovery losses, because otherwise you have a small short circuit on the low side transistor, and the losses at high frequencies are difficult to keep up with. So in that case, the GaN transistor or the SiC are well adapted for this type of operation. And you can increase the switching frequency without suffering too many losses. In the terminology of PFC, sometimes, or inverters as well, sometimes you will see a term called multi-level type of converters. The output voltage of a boost is selected based on the maximum peak input voltage, okay? And for 265 volt RMS single phase, usually a 400 volt DC output is usually adopted, but some applications which operate down to 85 volts, like on universal, can dynamically set different levels for improving efficiency. So from, let's say, 85 to 150, they set up the DC level at 250 volt, and when they detect that it's going into European mains, then they switch to 385 or 400 volt DC. And then with the two different operating ranges, the efficiency nicely benefits from this dynamic adjustment. In the three-phase application, the rectified voltage could peak close to 600 volts. So the DC bus is usually regulated at 750 or 800 volt. And you can imagine that this high level imposes severe breakdown constraints on the semiconductors and decoupling capacitors. We can split the DC rail into two voltages, 0, 400, and 400, 800, as you can see here on the right side. This one is called a two-level PFCs, 0 to 800. This one is called a three-level PFCs, 1, 2, and 3 level. And you can multiply the levels here. Of course, the converter gains in complexity, and determining the switching pattern is a more complex exercise. But at least here, typically in a Vienna is a three-level type of converter. You can use 650 volt semiconductors, while you would be constrained to 1.2 kV semis here if you would be building a two-level converter. The cool thing with three-level PFC is that it simplifies the stacking of power converter, which will operate with a lower voltage stress, of course, because they stack on two separate rails, 0, 400 and 400, 800, the total here being 800 volts. The floating outputs can then be combined in series or parallel to deliver more power. You can even interleave them if you want, as it is shown here for the PFC control. This example here never had a lot of success, considering the floating connection of the input source, naturally leading to an unfavorable EMI signature, but at least you can see the principle here of stacking power converters. It's very popular structure, at least the stacking approach in high power converters for EV chargers. In this three-level version, that's another one, we call it the T-type. The two switches are connected back to back, as you can see here. So one of the switches is always turned on in half of the input line cycle, while the other performs the high frequency switching action. So S4 is on during the positive cycle, and S3 switches at high frequency. In the negative cycle, it's the opposite. S3 is permanently on during the cycle, and S4 switches. The off-time voltage across the inductor is half of the output voltage, because it's a 3-level type of circuit, which means that in theory, for a given wanted input current ripple, the inductance can be half of that in a 2-level PFC. So you reduce the cost, the size, and of course the losses on the inductor. This resembles the single-phase version of a Vienna rectifier, as we will see in a minute. In that particular case, even if this is a single-phase example, you can see that the output voltage must be twice the peak input value, implying a 800 volt rail for 265 volt AC input. As, let's say, with any power converter operated in closed loop, PFC needs to be compensated. That's a closed loop system. You want to regulate the voltage at a certain value. And SIMPLIS, that you know I use quite often, lends itself well for running an AC simulation when the circuit has reached steady state. SIMPLIS, unlike other SPICE-based type of engine, is what we call a piecewise linear circuit. It means it treats nonlinear equation or nonlinear components with segments. Okay, so a diode would be modeled by two segments, one flat until you reach the threshold value, 0.6 for instance, and then going up with a slope, and that is the inverse of the dynamic resistance of the diode. And so when SIMPLIS changes from one operating point to the other, it jumps into a linear segment, and there is no need for a linearization process to take place, so the simulation time is flashing. And the good thing also, because you deal with a linear system, you can run an AC analysis directly from the cycle-by-cycle circuit. That's what you can see on the graph here. I was able to build a complete T-type PFC here. The source is still active. That's the beauty here. You can see the AC source is actually biasing the PFC. So this guy operates like if it was wired in the lab. And then with this, what we call the periodic operating point, SIMPLIS is going to determine what is the steady state. It means everything is stable and the transient period is over. All average currents in capacitors are approaching zero at the pico resolution level, and the same for the average voltage across any inductor. And once this is done, the noise floor is very, very low, and SIMPLIS can inject an AC perturbation, which is somewhere on the graph. And here, because owing to that technique, you can extract the open loop response and then run a compensation strategy here to cross over with, let's say, 4 Hertz in that particular example and 60 degrees of phase margin. So that's pretty cool. And you can see here the waveform and the envelope of the current and the 2 voltages with the split capacitor. One thing here, that because you have two different rails, usually you need to have an extra low frequency loop that is going to work on balancing exactly the voltage between these 2 capacitors. So that's an extra burden for the designer, but you have to be aware of that. Let's go for 3-phase networks. As I mentioned, the 3-phase world is a very vast territory, and there are plenty of structures to choose from, depending on the power level, on the application, or the skill of the designer. These are the 2 most common structures that I've seen so far. So on the left side here, you have what we call the 6-pack or B6 structure. It's found in high power 3-phase system. This structure is naturally bidirectional and can be scaled to several tens of kilowatts or more via an interleaved approach. Bidirectional means that you can absorb energy from the source, but of course, if this part here is the battery of your car, for instance, then you can send or you can reconstruct a 3-phase. So this guy works as an inverter to re-inject power inside the grid. Okay, so this is naturally bidirectional converter. The control strategy of the transistors ranges from a simple 3-loop arrangement, like if you were mimicking a single-phase type of structure 3 times, to more complicated space vector modulation scheme. The Vienna rectifier on the right side, it was patented in 1993 by Professor Johann Kohler. It was for Axis at the time, which is now Little Fuse. It's a 3-level converter, which, as I said, lets you stack power converters supplied from 400-volt DC rails instead of single 800-volt bus, as you can see here on this 2-level converter. The stress on the semiconductors is reduced, and you can use 650-volt rated components. And finally, the control of the back-to-back switches is simplified, in my opinion, compared to that of the 6-packs approach. However, in this very simple implementation, the converter is not bidirectional. And as I mentioned before, you need an additional loop for controlling the output voltage well balanced between the 2 output capacitors. So again, it adds an extra burden, but there are plenty of application notes you can look at. This one from Microchip is very well documented on the implementation of a Vienna rectifier. Let's have a look now at how 3 single-phase power factor correction is realized in single-phase networks. So, as any switching converter, a boost PFC can operate in different modes, depending on how the inductor current evolves within a switching cycle. We call it borderline conduction mode, or boundary or critical mode. It's abbreviated CRM or BCM, depending on the literature. It implies a variable switching frequency to keep the inductive current always discontinuous at the border, actually, between DCM and CCM. In absence of dead time, meaning the power switch is turned back on when the inductor current is equal to 0, then the average current is exactly half of the peak. Okay, and that's the cool thing here. You can see the peak current is here. The average here is exactly the peak divided by 2. The thing is that people usually here, they add a small dead time. So it obviously introduces a little bit of distortion in the formula. But by applying dead time, you can implement what we call valley switching operation and reduce the terminal losses. So if you impose a sinusoidal envelope in borderline conduction, so the envelope is this guy, the peak here, if this is a sinusoidal envelope, then obviously, because of the link between the peak and the average current which is absorbed from the source, which will also be sinusoidal, which is quite convenient. In CCM, the inductor current is always greater than 0, as we said, except near the 0-volt region, where DCM can be observed. And this operating mode requires an inductance value, which is, of course, naturally larger than in BCM, because you can't deplete the inductor cycle by cycle. But the core losses and the RMS current are reduced compared to BCM operation. The diode being brutally blocked in this type of circuit, you need a low TR type or a SIC device can be selected for the best efficiency and reliability. And finally, recent PFC controllers, transistors, transition between these three operating modes to improve THD and light load efficiency. You will see PFC that either within the sinusoidal envelope are going to transition between BCM, CCM, and discontinuous mode, or outside of, let's say, once a full half cycle is completed, then they're going to change the operating mode. This helps improving the efficiency in light load, but also the distortion within the sinusoidal waveform. So plenty of IP here on the operating modes. Constant on time control, that's a popular technique that has been used for many years, and you can find in low power PFC controllers. The instantaneous input power depends on the average input current, which is the average inductor current. So a few equations here show that the on time remaining the same for constant output power, but the switching frequency is going to move along the input sine wave. That's the drawback of these simple BCM PFCs. You can have very high switching frequency. Of course, you know that the switching losses scale with the switching frequency, so there are plenty of different schemes to hold the frequency back depending on the operating condition or the region where you stay in the operating wave. So the left side expression shows that the input current will follow the input voltage shape affected by a constant factor scaled by the on time itself, adjusted by the control loop. We can have a look here using SIMPLIS, and as I said, SIMPLIS lends itself very well for flashing simulation times of PFC. So this is a boost converter operated in a self-relaxing quasi-resonant operation. Also, as I said, it's known as boundary operation. I say self-relaxing because there is no clock inside. It's just based on the detection of the core reset event. So it means depending on the input and output conditions, you will have different switching frequency. There's a dedicated winding across the power inductor, which helps detecting the valley voltage and restart the switching cycle when the inductor is demagnetized. And you see this current distortion, the fact that the switching frequency can go very high, especially when the voltage approaches here the 0 volts. So the switching frequency goes up, and you can have a zero crossing distortion. Again, there's plenty of technique, like some of them are adding a small offset or to force a larger T-on approaching the zero crossing line regions. So it helps improving the distortion. But again, by using SIMPLIS here, I can first of all test all the waveform, look at the RMS current. Here I can replace this guy here by a downstream DC-DC converter and look at the total RMS current, which is made in this capacitor by the low frequency component and by the high frequency switching cycle. So this one here was voltage mode control. As you can see, there is no, here in voltage mode control, there is no input voltage sensing. Okay, but if you go back to the equation as shown, without sensing the input voltage, I can generate a very good power factor. A peak current mode control, it was implemented by Motorola in the early days. I think it was before the 2000, the 261 and then the 262 featuring an OVP was released at the time. Here you have a multiplier, so you take a portion of this rectified envelope here, this one, and then you scale it with the multiplier and the error voltage. So This image here is going to be put up and down here to force the envelope on the inductor current. So that's a fairly easy way to control the electronics here. Average current mode control, it's another technique. So before that, it was borderline operation. Roughly, borderline control allows you to go up to 300 watts in single phase. You can interleave and go up to higher power levels, like 600 watts, for instance, but usually it's the limit 300 watts. People like it because you can use a lazy, between brackets, diode on the output, and because this is a discontinuous conduction mode, you don't have the TR related losses on the switch. In average mode control, no, this is CCM, so you need to have here very good quality for the diode and probably very fast switching transistor to avoid the overlap of current and voltage at that turn on. The set point here is given by the multiplier output, and it imposes a current in the OCP resistance because we have negative sensing here. And together with the sense resistance, these two resistance, the OCP and sense, they set the maximum inductor peak current. And the set point is made sinusoidal through the sense of the input voltage multiplied by the error amplifier, and it scales the inductor current to deliver the right amount of power. This is a two-loop system, and it needs proper compensation, and you can run small signal analysis on either on the outer loop or on the high frequency current loop, which is here. This one has a crossover frequency of a few kilohertz. This one, of course, still has the low frequency limit of a few hertz. And we can show, mathematically speaking, that the small signal response of the power stage includes the contribution of the square input voltage. So the square VAC. So it means that low line and high line, if there are no compensation schemes inside the circuit, the crossover frequency will change. So that's why you saw in an integrated circuit like the UC 1854 years ago, they did include a divide by Vin square for compensating this power stage AC response and to make it independent from the input line. Sensing the high voltage rail, it implies a high voltage component and a permanent loss because you can go up to 370 volt DC on the rectified voltage, at least if this is a DC voltage. But as exemplified in this particular foil, it's possible to build a power factor correction engine by generating enough time duration which is proportional to the average inductor current. And this was described by Sam Benyakov, well known from the audience. He has a very nice YouTube video channel. And he described the technique at the time in which the off-time is naturally modulated without sensing the line. So he patented this circuit in 2001. And it was actually about changing the slope of the capacitor here to modulate the off-time based on the error voltage. It's a very neat and very simple integrated circuit, as you can see here. And I was able to simulate it, first of all, using an average model, using the PWM switch model from Vachiev-O'Brien. And here in LTspice, a bunch of control sources here. This is an OTA, a type 2 compensator. Everything is automated here for the calculation of the compensation elements. And there you go. You can run the simulation in LTspice, and you see this is the AC response you can obtain from that average model, and you can calculate the compensation element here. I've got a 77 phase margin with a 3.3 hertz crossover frequency. And then I can use that average model, which is the cool thing, because this is a large signal average model. So it means SPICE will linearize it anyway to extract the AC small signal response, but I can use it for real simulation with a sinusoidal waveform here. And because it's an average model, there is no switching components, and then it means the simulation time is very fast. So I can test the compensation strategy that I have adopted for crossing over at a certain value and see the impact on the distortion and the transient response. Of course, when you do the cycle by cycle version, you will factor in different kind of things like distortion linked to the high frequency going up, to the switching losses and everything. But here you can see already that the crossover frequency is what we wanted to have at low line, but here, because there is no compensation of the power stage gain, as I said, in high line, of course, you have a faster transient response at high line than what you have at low line. But you can see it's fairly stable, which is cool. And you can explore the different scenario here just by changing the components value. You could change the crossover frequency, which is here. You can put a different value, for instance, and immediately see the impact on the transient response. I've used that technique to build TP PFC, totem pole PFC. So you can see the fast leg, which is here. When I run simulation, I always start with a very basic and very simple circuit with perfect components, of course. And when it starts working, when I'm happy with the results, I will then replace these guys with a proper driver, bootstrap perhaps, MOSFET transistors and everything. So that I know my structure operates correctly. And if I put or drop in a component and suddenly it doesn't work anymore, I know that this part that I've added is the guilty of non-convergence. Rather than starting from scratch with a very complicated SPICE models of everything and then it doesn't work, you don't know who is the guilty. Starting small and then increasing the complexity and the comprehensiveness of the models is the way to go if you want to have, let's say, a well-running simulation and not losing time in debugging the circuit. So here, this is the TP-PFC. You can see the inductance, which is here, which is floating, connected directly to the input source via filter. I could have here a Hall effect sensor, which is here, and I'm sensing the current through this technique here. So this is, I'm taking the absolute value. I need to have always positive type of information, and it's going through the amplifier here. And I used a simple diode bridge that I can later on complexify that circuit to deliver, of course, synchronous low frequency synchronous rectification pattern for these two diodes. This is what you have inside the PFC, a dead time, of course, because you are actuating the high frequency in a half bridge type of circuit. One of them is the power switch. The other one is going to be the rectified diode, and then it's going to toggle here depending on the input line polarity, which is detected here, and this is the PWM routing depending here on the line cycle. Of course, you need a robust here detection circuit, and that's the thing you may want to look at when you select a driver. But because depending on the distortion, depending on the surge, it has to properly route the good signal to the PFC. An alternative approach for this TP-PFC is the bridgeless structure, which is also another type of circuit where you don't need to detect the polarity, and you can also obtain very good efficiency. The uptime modulation is here, and there you go. If you run the simulation with LTspice, it's fairly fast. You can see I have an old machine, which is a Core 7, but it's still 15-year-old machine. Around 3 minutes, which is acceptable to see the operating waveform. I can extract, of course, the average and RMS constraint and everything I want. I can also run the same TP-PFC using SIMPLIS, and I can extract also the AC response and compensate the circuit without resorting to an average model. That's a very interesting thing as well. So if you have an average model, you need to go through it using LTspice. You could tell me, well, LTspice has the ability to do frequency response, to be a frequency response analyzer as well. It's true. However, especially when you want to look at very low frequency crossover values like a few hertz, you would need to simulate many switching cycles before being able to extract meaningful data at these low frequency values, especially when you switch at 100 kilohertz. SIMPLIS doesn't have that problem. You can extract the AC response almost down to DC. And you see here, I've compensated the PFC, and it's a very good response. So the AC source is turned on here. That's the cool thing. I can use that circuit, stabilize my whole PFC device using the same approach. Here I'm using, this is the absolute function that I've built here using a diode bridge, perfect diodes. Then this is the sense resistance or the the whole sensor value going through the amplifier and going inside the sub-circuit was the same structure that I showed, that I shown on LTspice. There has been a few implementations for integrated circuits that could provide sinusoidal input current without sensing the voltage. And the NCP 1653, it's another type of what we call predictive control. In this type of circuit, a ramp is classically created by having a capacitor C ramp charged by a constant current. And the power MOSFET turns off occurs when the ramp voltage intersects with the reference voltage VREF. The ramp does not start from 0 volt in that case, but it sits on the voltage component Vm, which is the absolute value of the sinusoidal envelope involving the inductor current. And this envelope will be scaled by the static input voltage value and shapes the offline variation imposed by the control engine. This technique, which has been introduced by my friend Joel Turkey at onsemi years ago, has been extended and perfected by adding frequency fallback, smooth transition, and different operating scheme from transitions from CCM to DCM. The TP-PFC NCP 1681 from onsemi, for instance, operates in this way also. In this example, you recognize the PWM switch model operated in voltage mode control. The control law, however, which is here, has been here built to mimic what you can see on the right side, which reproduces exactly what you have in the NCP 1654. And I used an OTA here. This is a type 2 OTA, right? Type 2, if you remember that. Type 1, 2, or 3. Type 1 is a simple integrator. Type 2 also has an integrator, but supplemented by a pole zero pair. And type 3 is also an integrator, but supplemented with a double or dual pole zero pair. And by adjusting the distance between the pole and zero, you actually change the phase boost you want for stabilizing your circuit with a given phase margin. Here, the average model simulates extremely fast, as you can see, and I can test the overall performance like output ripple and low frequency RMS component as I shown before. If I change the crossover frequency, I will have a faster system, but more ripple will go through the raw voltage and I will have more distortion or THD. This is the way you can, the average model, as I said, it's a nonlinear model, it's a nonlinear subcircuit, but SPICE is going to linearize cycle by cycle the device, and I can extract the small signal response even with a nonlinear circuit. And I can take a look at the compensating response here, which is 4 Hertz, 68 degrees of phase margin, and the transient response in case I have a load step. So the whole thing here can be simulating using LTspice or SIMPLIS almost from scratch, from the design circuit to the fully stabilized operating circuit. Now we're going to see a few solutions for three-phase networks, and needless to underline that this is a very complex and vast territory with many difficult trails. We'll only explore here a few here just to give you an idea of how complex it is. So it's possible to use the classical fixed frequency boost structure, which is adapted to a three-phase application. And in this mode, the current distortion is quite high. So you can see you have just one single inductor here, the three legs of the diode bridge, and here a switch which is activated with the constant of time, the variable of time technique. And you see the THD here. You have, because of the holes here, we'll see in a moment, you have holes in the conduction diodes, the conduction time of the diodes, and the THD is very poor, 35%. It can be used for regulation purposes, for instance, but not for having a nice THD. But it's simple to implement. Now you no longer have one inductor, but you go with 3 individual inductors. And this guy here is operating in what we've seen before, the borderline operating mode. And operating in borderline is fairly cool because if you truly have constant slopes on the inductor, then if you set the peak, the average is half of the peak. That's the beauty of the BCM operation. Alas, here in three-phase, it no longer works the same way because you have one of these diodes which is going to conduct at a moment and then force a different downslope. So as I said, you no longer have constant downslope here. And even if you have a very nice looking sinusoidal envelope, because of non-constant downslopes in the inductor current, unfortunately, you don't have sinusoidal input current. This is an application example of this free-running technique, three-phase, and three-phase PFC. We deliver 3 kilowatts to a load, and we use one single switch, and the RMS current in the transistor is 3.8 amps for 400 volt AC, phase-to-phase, of course, with peak current reaching around 13 amps. And this circuit includes a specific circuit to limit the maximum switching frequency, and also what we call a watchdog, because this is a QR type of operation. So in case the restart operation doesn't come in time, then you have a watchdog restarting the circuit. It's a 10 kilohertz watchdog, and it's very common to classical QR converter. And in this simulation, surprisingly, the THD is about 12%. And again, these are classical waveforms you can find in the literature. It's considerably lower than the first single switch boost converter, but it's still fairly high. In the balanced three-phase network, the input waveforms are delayed by 120 degrees, implying a certain combinations of polarity at a given time. And we can distinguish different sectors to identify the phase voltages. And these sectors are usually numbered from 1 to 6. And in sector 1, for instance, the phase A is positive here. Phase A is positive. And activating switch SA would let you increase the current and classically boost the voltage via D2 as a catch diode. However, phases B and C are negative. Body diodes of SB and C permanently conducts, and actuating SB, SC at the same time would be useless to impress a given shape because the diodes always conduct, right? And now in sector 4, we have two positive phases, and we can drive switches SB and SC for impressing the desired sinusoidal shape. So theory states that if you can control two phases in the balance system, the current in the third phase is automatically controlled, considering of the sum of the instantaneous currents being equal to 0. And as shown in this example, this would only be possible in selected sectors, confining this structure to regulation purposes only. Now we change the diodes by control switches, and this six-switch configuration, which is known as 6-pack or B6 structure, is a popular architecture in high-power three-phase power factor correction modules. Several techniques exist to drive the power switches at moderate switching frequency for IGBTs and up probably to 30-50 kilohertz for SiC transistors and power levels of 20-30 kilowatts or beyond. The structure can be interleaved to spread the power dissipation budget on more semis and reduce the stress per transistor. And we're first going to look at the 6-step modulation technique, which consists of turning off one leg while the remaining two are active. It's because of the sectorization that I've discussed before. And in the balance system, the third current will naturally be controlled, considering the sum of all three-phase currents being equal to 0. So let's see what a 6-step modulation implies. If you look at the sinusoidal waveforms in the upper right corner, you see that in some sectors, one phase is positive while two are negative. And this is the same situation that we described in the slide that we've seen before. And as a result, in sector 1, the body diode of SAP will permanently conduct, and you cannot control the current of phase A in this period of time because the diode is a short circuit. The same situation arises in sector 4, where the body diode of switch SAN will conduct, and you cannot control the current in this phase either. As a result, the logic block will disable leg A in sectors 1 and 4, leg B in sectors 3 and 6, and leg C in sectors 2 and 5. And this is exactly what I've done in this foil. You can see a three-phase PFC configured in the 6-pack architecture with individual phase current shaping. So this is the concept of average current mode control used in single phase here, multiplied 3 times for a very simple type of control. The error voltage scales the amount of high frequency current imposed to each inductor via dedicated multipliers. I could have used average models to extract the control to output transfer function of this power stage, but I used SIMPLIS to extract the AC response, and it delivered me the right power stage AC small signal body plot in a few minutes. And type 2 OTA is compensated for 100 Hertz crossover frequency. This time with three-phase PFC, you're no longer constrained to have a low crossover frequency at a few Hertz, so inherently slow type of response. Three-phase, you can push crossover slightly higher. Here I was able to meet 100 Hertz crossover frequency because of the lack of low frequency ripple. And the simulation here is good. I've got a THD at full power of 3.9% in this very simple application scheme. The power is set to 12.5 kilowatt in this region here, and then we jump to 25 kilowatts, and you can see a very good transient response. It's an 800 volt type of application. Okay. DQ0 transform. The difficulty with three-phase systems, and it's a complicated matter, but I can try in a nutshell to explain this approach. But in a single-phase PFC, we have only one single AC source. And we have seen that it's relatively easy to shed the input current sinusoidal way while ensuring a zero phase shift on the input current. Three-phase networks, we have three AC sources, and they all shifted together by 120 degrees. And we want to ensure output voltage regulation while absorbing a sinusoidal current and keeping the reactive power to the lowest on each phase, or controlling the reactive power in some application as well, because we shoot for Q equals 0 for the vast majority of cases, but there are plenty of applications where you want to have a different Q and force an impedance to be either inductive or capacitive. So it complicates the architecture. One possibility is to transform the three variable input voltage into two DC components representative of the active power. This is what we call the D component, and the reactive power, which is the Q component. This is called DQ0 transform. So D will be imposed for a given P out, while Q is kept to 0 or adjusted in some cases. The way to go from a three variable frame to a two DC component system is to use what we call the DQ0 transform, which is made of the Clark and Parkes transformation. And of course, once you have your regulated signal, you're going to use the inverse transform to deliver this new set points that you're going to send to the modulator for imposing the sinusoidal waveform to the input sources. Processing the DQ0 signal requires the access to input current, but also the theta angle computed via phase lock loop synchronized to the input source voltages. In this example, since we want the reactive power to be zeroed, we set IQ equals 0, while ID, which is here, is going to be adjusted through the error voltage. So you have three loops in these examples: the voltage loop as a classic in PFC, and then the D loop and the Q loop, and each of them has to be independently compensated. I've set the voltage loop error amplifier here to crossover at 20-30 Hertz, but the two other variables are stabilized with the type 2 compensator, and I'm boosting the phase around 2-3 kilohertz. It's usually digital control type of crossover frequency that people are shooting for, especially if you look at this seminar, which is a very instructive one on three-phase modulation and three-phase type of control. The inverse orthogonal transform, which is here, is going to create the current set points A, B, and C, and they are modulated via three comparators and a 30 kilohertz here, triangular carrier. Some dead time, of course, is inserted here because we are controlling these guys with Q and Q bar, and we try to reduce the shoot-through current. I used here, I couldn't use SIMPLIS because there's a lot of trigonometric type of operations here, but so I had to go through an average model, and I used the PWM switch model introduced by my friend Vachev years ago, and it lends itself very well for being used here in the three-phase application. I've extended that. You can explore that through my web page. I've extended that to a Vienna rectifier where you have 6 PWM models to extract the small signal response, and I could stabilize the loops, as you see that in a moment, and you can see that the transient response is very, very stable. So this is the way you block one loop while you inject into the other one. Very important when you do that, you need to make sure that the DC operating points calculated by the average model are correct, because GIGO, garbage in, garbage out, you can have a bad operating point and then still SPICE is going to give you an answer, but it will be correct. So when you run the AC analysis and you change one of the components from the circuit, always check that before considering the AC responses, the DC bias operating points are correct. And this is okay. I have a negative voltage here for D, very small value here for Q, and then, well, meaningful set points here. I've got a carrier between -3 and +3 volts, so it's okay. And here, the op-amp is correctly regulating at 2.5 volt DC. So I can consider now the AC response. And there you go. I can use the AC response from this circuit to stabilize the loop. Usually the Q and D loops are similar, but here there is a little bit of interaction because I kept, obviously, the voltage loop closed while I was AC modulating the TD loop. And the crossover frequency is about 2 kilohertz with a phase margin almost constant at 60 degrees. So it's a fairly cool design. I can then run a cycle-by-cycle simulation with SIMPLIS. And what I will do is I will compare the cycle-by-cycle simulation results to a transient step and compare that transient step response with that of the average model. If the average model is correctly done, then you should have perfect superimposition of the average model response with that of the transient model. And this is what you can see. And usually it's a relief when you see that. It means that your modeling is correct. And you can see there is almost no difference between here you see the average model, there is no switching components, and the cycle by cycle component. And the same for the output voltage. This is loop reacting to control the delivered power during the load step. And here this guy reacts to control the Q contribution. So it means the reactive volt amperes to be kept to 0 so that you have a good power factor correction. I can also run the model in LTspice. This time I've put real SPICE models of SiC transistors, and then you can run and enjoy, of course, the response using LTspice. Before you bring a model in, make sure that the model of your SiC or GaN or silicon junction transistor is correct. And I do that. I validate the model very briefly by using the double pulse test circuit, which is used by SiC manufacturers to actually show that the switching losses are kept at the very minimum. So the principle here is to impose very briefly continuous conduction operation on the inductor. So you have a first pulse here that turns the switch on. The inductor current goes up here to a given value, and that given value here usually has to match the datasheet parameter at which the losses have been measured in the lab of the considered manufacturer. So maybe something like 50 amps. I think it was about 36 amp in that particular case. And then you wait a little bit, and then you restart the power switch on the low side, while this guy here is actually recovering. Okay, it's like in a PFC stage. So when you interrupt the current in the inductance, is going to freewheel in that mesh here, and then suddenly you force the blocking of the upper side diode here. It's a hard switching operation, and then you have a big spike here because this guy here is a very brief short circuit until it recovers its blocking capability, and during that time you have a loss. And then you can, by running LTspice, by running the instantaneous power, so you multiply the drain current by the VDS voltage. You have peak here, you zoom in, and then you control plus left click on the trace name, and you can have here the average value of this guy. And this average value multiplied by the on time gives you more or less the energy lost during the off to on cycle, but also during the on to off at the turn off. And you have to look at the spec given in the data sheet. And if your SPICE model or if your SPICE simulation result approach more or less what the data sheet tell you, then it's a good sign that the model is okay. Just one comment here. People very often consider SPICE simulation for switching losses assessments. It's a very tough exercise. I would say you can have a fairly good confidence when you determine average or RMS current using SPICE, okay? But when you do switching losses analysis, you normally have to include the power distribution network contribution. It means all the stray inductance, capacitance you have because of the PCB layout, because of the parasitics on this capacitor here that is going to decouple the high voltage rail. And also the inductances, if the SPICE model is well modeled, they are included inside the model, but the bonding inductances and this kind of thing. And this truly complicates, first of all, the simulation time, but also the parameter extraction that very few people do. So be very careful when you consider switching losses with a SPICE simulation. If the power distribution network is not, let's say, well characterized, it may give you, let's say, an idea of what the total losses of your transistor will be, but it cannot replace the measurement in the bench and in the lab, of course. The Vienna rectifier pushes the bar a little bit higher in terms of analysis, of course. And you can see here now, I've got the two back-to-back or the three bidirectional switches here that can be replaced by MOSFETs once this model has been tested. I'm using DQ0 modulation. I have another circuit where I implemented space vector modulation in LTspice. And here to extract the control to output transfer function, it was a bit of fun to let's say determine it using 6 PWM switch models. So it's a heavy burden on the simulator shoulders because it needs to find the right operating point. And here it's key to exactly look at the DC value you obtain to really consider that your circuit is in regulation. But it works. And I've got the same here implemented using LTspice. And you can see here, I'm not sure, I can't read the part numbers, but these are two SIC models from Infineon, I think, or from ST, I don't remember. But I use them here using a simplified drivers. Of course, this is just for simulation purposes and the example. It's key for, let's say, proper simulation to exactly model the driver structure you're going to have for driving this SIC, and not only the on and off voltages, but also all the parasitics you will have in the drive path, like the stray inductances and this kind of thing. And then I also have built the average models. So you can see some of these models here just disappear when you select what will be the time at which you freeze the DC operating point. It's just because in some cases, some of these diodes here will or will not conduct. Okay, so and that's why you have one of the active PWM model that is some of these models that are active or turned off. And once you do that, then you can extract the small signal response here and run compensation exercise on the outer voltage loop here or on any of the on any of the two remaining loops here for the D and Q loops. There is another, I think it's on, if you look at my webpage, there is another simulation where I simulated an NPC, right, a neutral point clamp converter. And it's a 3-level type of circuit. But I did also on the Vienna. I took inspiration from the microchip application notes that I referred before by building an extra loop here, observing the voltage across the two output capacitors. It's a low frequency loop, low gain loop. Then you can control the zero input here of this inverse modulator to balance the voltages between the two capacitors. And I've run the example in LTspice and it worked fairly well. You can see that during a transient with and without the loop being turned on, you can see the very good action of this loop compensation action. And if you run the simulation, it's very fast here, and you can see the nice looking sinusoidal waveforms on this Vienna rectifier. The loop here regulates to 400 volts. Of course, I've got other examples where the voltage is pushed to 800 volts, as in a typical classical case. Almost there, almost the final slide. So we've seen that PFC is a hot topic for many decades now. And it's single-phase applications. There was a lot of controllers. Analog implementation is still possible. We still start seeing a bit of digital control, especially in the compensation path. Why? Because in the compensation path, people would like to integrate as much as they can the compensation elements. However, because of the fairly high time constant, it's difficult to reproduce these time constants in an analog way. So what people do is they hardwire digital control or digital compensator inside the chip, where it saves you from having this external compensation elements, and it's a more or less plug-and-play type of circuit. So different techniques are available with or without input voltage sensing. The one that I described was what is called a predictive law. You have a fairly good amount of ICs that do that these days. For example, the TP-PFC, it gains traction, as I said, because of modern semiconductors like GaN or SiC transistor, and it's actually very popular in very compact and very high density AC to DC adapters. Three-phase PFCs, needless to tell you that this is a very complex matter. And when I looked at it a year ago, I had difficulty with the terminology used in three-phase PFC. And the key here, if you want to go into three-phase PFC, is to start with the rotating machines first, okay? Because the rotating machines and motors, all the terminology, like symmetrical components and this kind of thing, are coming from that field. And once you understand where this terminology comes from, then you can start reading papers on three-phase PFCs. In most of the three-phase PFC projects that I've seen, they deal with digital control. Honestly, there's a few analog type of control, but usually it's digital control, especially with the extra burden now asked by the utility to have a system that is able to either emulate a true resistance or add an inductive or capacitive impedance components to the load for grid regulation purposes. So usually it's done with digital control. And simulation, as I said, helps a lot for assessing losses and this kind of thing, but also very conveniently for closing the loop. If you have the right average model, if you understand how it works, then you can do that. So I would like to thank you very much for your time and attention. As a final slide, you can download all the models, and the folks at Omicron will make this PDF available. There are links here. You can go to my webpage and have a look at the books that I published on the subject. I published the 10th book in September 2024. And then if you go there, you can download all the PFCs in single phase, but also three-phase approach with all the examples in single phase and three phase. You also have LLC type of controllers and many interesting documents to download, and everything is free, of course. Thank you very much, and I'm sending the control back to the folks at Omicron.